For this box, they have given the name my box. It is made from TS box, which we will look into this detail, like what kind of uh, TS box is one geometry type that Topaz provide. There is spheres, cylinders, cones, and different geometry shapes that you can use and uh, play with them to get your exact simulation equal to your measurement or um, uh, experimental setup. You can just replicate your experimental setup using the basic shapes and applying intersection or union or any kind of like Boolean expression to them. So, yep, here it's x dimension, y dimension, z dimension. So here you see h means half length. It's not the full length you define. So you just define the half length, then you define there if you want to translate it from the central axis of the world volume or not, and if you want to rotate the box or not. So it's 0, 0, 0. Now is the physics list. So once you define your geometry and you want a setup, you want to track any kind of particle, you need the physics settings. So here we'll be talking more on this, but here it's standard option 0 gene for electromagnetic physics list that they are using, or physics setting they are using. And this view A is basically a way how you can define your own viewer. Like this comes from OpenGL, is a kind of a mm, graphical user interface that you can use with Topaz and interact with your simulation setups that we will be doing in our future uh, uh, sessions. So now, yep, when you run your simulation, so it actually starts like this. So like I mentioned earlier, you had to get your own license. So the line starts, every user must have their own individual valid license to run Topaz, but now it's not the case. It's open source, so you might not be seeing this sentence. And then it defines like where you have added your gene for data. So we will get into this detail as well, like we discussed yesterday. Topaz is a kind of a wrapper over gene for Monte Carlo code, so to make it more user friendly to and more accessible to the medical physics teams. um, Lastly, yep, this is how the screen output you will see when you run this command from your computer on where you have already installed Topaz. So now talk this understanding how Topaz is organized or formed. So basically, Topaz, like I said, is wrapped over Gent4. So behind the scene, what you are running is Gent for Monte Carlo code. And in Gent for Monte Carlo code, you will be including all the details or all the Gent for data files that you will be downloading when you download your Topaz. You will be also downloading these files like I show you here. If you go to the user guides and you go to the installation guide, so first you install the prerequisites, then you download the Topaz and try to install it. So you'll be just focusing on these Debian files or for Ubuntu. Lastly, see, you install data files. So these data files are actually nothing but the data files from Gent4. So, and you will be downloading directly from here. And you see, these are Gent4 data files. So Topaz is directly wrapping Gent4. So actually, behind the scenes, what you are working with is Gent4. So let's get back. Yep. So you will be using the information that has already included for basically developed for Gen 4, and so Topaz behind the scene uses Gent4, and how it works, how you use it. You define your parameters in a text file like I just showed you for what single box. So we will be defining our geometry, we will be defining our physics, then we will be defining our scorer that we call as voxelized grid that I just showed before in my first presentation when I was defining, like I show you again.
The
Um,
mesh with the
yes, exactly, exactly. So first, for defining the geometry, we'll be defining this shield and then
shield.
the
Yeah, yeah.
seed. Then we'll define this grid. And you see this outer boundary of extra white line. This is
Yeah.
actually our world. I have defined just a world volume that is good enough, big enough to include our all the geometries.
Okay.
So you don't need to have a very big world. You can just see the thing is as you should maintain the size. Your world size should be big enough to include all your experimental setups, but small enough that but it should be well managed. Like it should not be too big. It should be that much big that it includes all your geometries within it. Okay, so this will be doing, and yep, thus we will be learning how you define your parameter files like uh, yep, like geometry, physics, scoring, and visualization. Like I just showed here in the basic example of Topaz, they define the geometry, physics, and the graphic user frames. And pause before quit is just like if you run this command, and if you don't put it like true, so it will just exit and you will see nothing. So if you want to see your graphics, you should keep it true. Okay, so
Okay.
we'll see
Okay.
this in the future. So like I said, in Topaz parameter file, we have geometry, particle source, physics, then scoring. Scoring is what you want to calculate, then graphics, and time feature is basically like that includes you will be using time feature. You should be able to simulate experiments like
The dual.
like
Yeah.
brachythermy experiments.
Yes.
So do you have any question?
No, I was just talking about the time feature, which corresponds to the dwell time in
Ye-
brachytherapy
Yeah,
plasma.
and even like breath hold techniques or such treatments can also be simulated using this time feature. And
Yeah.
also, like I said, all the details that I'm presenting here are taken from the Topaz website. So here I've just cut pasted, took a screenshot of some of the main pages where from where I took these collected this information. So you can you yourself, if want to you wish to check these information, you can directly go there and get things in more detail, because 10 hours is not good enough for getting the
Yeah.
complete information about
That's
how things work with Monte Carlo simulations. So here, like I was telling you that I will be presenting one example of the Monte Carlo simulation study that we did and we published. So here we calculated the dose point kernel, which is basically is a energy deposited along the central axis of a sphere. So what we consider is a very big sphere, and inside this, which we called our world, inside this world we defined uh, series of concentric shells which looked like this, and And we place the isotropic point source at the center of the central sphere, and we calculated energy deposited along the central along in each of these shell, concentric shell, which is the mean energy deposited, and based on that we calculated this energy deposition here, which I have presented in this graph. So I'm showing like how you are going to do your simulations. So it's just a first
Okay.
example or first look on how things are going to be.
Okay.
So first you get an idea what you want to do. So you clearly know that we want to estimate the energy deposited along the radius of a water sphere from an isotropic point source, that is a radioactive hafnium 166, which is placed at the center of the water sphere. So now the question is how we are going to do this calculation. So first we need to define our radioactive source. Then the question comes how big this sphere should be. So we don't need a too large sphere, sphere with the radius 1.2 times of CSDA range of the electron emitted from hafnium should be good enough for this calculations. So this is how we define our world. Then uh, we decided to divide the simulation or the sphere into 28 shells. Maybe you can do it for less number or more number based on how detailed information you are expecting, like what voxel size you want to work on. Maybe you want a big one, or maybe you want a much smaller voxel size. So these shells are just nothing but spherical voxels, you can say. And we
Okay.
calculated the mean energy deposited and the standard deviation in these calculations. So these are the our minimum, our maximum, and we defined our medium, like middle of mean of this. And we calculate found from like literature that the maximum electron energy that hafnium deposit emits is 1.854 mega electron volt. Then the CSD range of this monoenergetic electron is around 0.89 centimeters. And if you calculate 1.2 times of CSDA, it gets to be 1.07 centimeters. So we defined our spheres based on this and shells based on this data. And then we defined our world volume. Like I said, its Topaz geometry definition is very data type. It's very much bind with the data type that you want to use. So here it's double to define the half length along the XYZ axis for the world volume, and we don't want to see it, so we just set invisible equal to true, and we define the material of the world as vacuum. And then we defined our the complete water sphere, and then the shells or these shells are similar to the yellow grid. First, you define your big water phantom, and inside that, you defined another scoring volume where you want to do the calculation or where you want to do the scoring or storage of the calculated dose or the values, or what like maybe the photon fluence or electron fluence that you are interested in. So this is how first you define your world, then you define your own geometry. Like in the system that we will be using as an example in for you will be like your world, then it has three geometries. One is the shield, then there's the seed, and then is the water box. So similarly here we had sphere, the world volume that is blue, and these shells. So these shells are in which we perform the calculation which is equivalent to this yellow grid for you in your, which we will be using in your tutorials or your studies. And then yeah, so this is how you can define your geometries. Of course, we'll be going more in detail in our next session on defining our geometry. For that will include our shield, seed, water box, and yep. So we will define these three together in our
Okay.
next session. Okay. And if you want to get more knowledge about what different geometries you can simulate, you can check the user manual of Topaz and Gint for and get more detail on this.
Okay.
And then it also provides, like I just showed, it also provides the idea about how you can define your different volumes. Like here, I took a screenshot from the Topaz website on how you define the material and or the world volume and set its dimensions, like we discussed, translation along x-axis and rotation xyz axis. So you
Okay.
can set whatever you wish to. So there are different, like what is the parent of the volume, and what is the translation and what is the rotation. Next comes is physics settings. Like I said before, different experiments need different kind of physics list. If you're working with low energy X-rays, high energy X-rays, electrons, protons, or other ions, carbon ions, so such as, so you will might be needing different type of physics theories. Like now your question might be like why there are so many physics settings, because physics is one, and don't we need just one physics uh, list, and that should be good enough for our all our simulations? Yes, but there are different theories, and these physics list or these physics uh, settings are derived from these different theories that are available in literature. So, and each of them has a different uh, l- boundaries, like the lowest energy that you can simulate and the highest energy of electron, photon, or proton that you can simulate using these uh, settings, or these we call it physics list. So based on, so you have to choose it very carefully which one you should be going you should use for your calculations. Okay. And yep. So now scoring the source definition, so you can define your source in the form of a beam or emittance or isotropic point source, volumetric source, or phase space. We'll be looking this more in detail in future tutorials, but I provide you an example of how you define isotropic radioactive point source. So first you define you call it like the source you are going to define is isotropic. It is a beam position type source, and here beam position is, it's the component of beam position, or you can say um, the geometry that you have already defined, and then which type of particle you want to simulate, so electron. Then since we are using a radioactive source, so we have to define what is the kind of spectrum you will be using, so it is continuous type. First we define the energies of the particle, then their weights, and then how many particles you want to simulate. So here we simulated 5 million particles just for example, but at least when you run uh, a calculation with a minimum statistical error, it should be around 1 billion, and which requires a lot and lot of uh, computational resources. You won't be able to run big huge simulations on your laptop.
Okay.
And you can also, as I said before, you can get more information on the source definition from Topaz website. We will get into this in much deeper. We'll get much deeper into it in future sessions. And similarly, you can calculate those fluence, surface current, phase space, and other things. Phase space is nothing but it's just like getting a knowledge about each and every particle, its position, its energy, its momentum, and that you can use in your future. There is a way that you divide your simulation into two or three parts to handle it efficiently and minimize the requirement of uh, computational resources that you need, or if you don't have a supercomputer access, or um, any source of resources that you can use to perform your calculations efficiently. You can divide them into series, divide them into like three, four parts and do one, two, three, and then you sum up all the results. So this is another way to do the calculations efficiently.
Okay.
So here I have shown an example of like how you can calculate the dose. So what we want to calculate the quantity is dose to the medium. Which component we want to deposit this dose is on our shell one, and it's nothing but the output type of the file. We want to get the output in CSV file, which is nothing but an Excel sheet. And what should be the name of the output file is this, and what you want to report. So we want to report the sum, mean, dose, and the standard deviation in the calculated results. So we want three values, and the more information, like I said, you can get from Topaz website. We are only focusing on things that will let you get started, and after that you can start working on your own and start looking for more advanced things to work on. Okay. So yeah,
Okay.
this lastly, the graphical user interface, how your simulation setup. Of course, like once you set your geometry, you set your physics, you set your scorer. Maybe you wish to check like what my simulation looks like. Maybe it's not the exact what you were expecting. So in that case, this graphical user interface come are very handy. You can define like what you want to see, what particles you want to track, and you can give them different colors. And so it is really very helpful when you'll be doing your own simulation. You will see that graphical user interface is something that you really need for your simulations, and to design your simulations more efficiently and correctly. So here also you can get more information on the graphical user interface in the Topaz website. Yep. And like I said, I got all this information from the Topaz official website.
Okay.
So, yep. Mm. So is there anything, do you have any questions of whatever I have presented?
I think for now,